Hello. This talk is about computation and applications of Mathieu functions from a historical perspective. My name is Rob Corliss. So let's just get started. On the left here we see an animation of a particular mode of excitation of a vibrating drum, a vibrating membrane on a drum, where the hoop that's holding the membrane fixed is of an elliptical shape of ratio 5:3 actually. And this particular mode is got 13 ups and downs in there and oscillates fairly well. So, all right, there's lots and lots of different modes that you might see on here. Who did the theory for this? Émile Mathieu in his paper from 1868. If you get a copy of this workbook, then it'll have a link to a translation of that paper, but that paper is also online. We imagine that we have a membrane that's homogeneous in all directions and held fixed on a contour, immovable on the contour, where the contour is an ellipse. The goal of that particular memoir was to determine by analysis all of the circumstances of the vibratory movement of the membrane. And in particular, Mathieu was interested in calculating what are called nodal lines. The nodal lines are the places which don't move. If you look at the vibrating thing on the left, you'll see that there are lines where the membrane doesn't move. Maybe it's a little bit easier to see if we look at it edge on, but yeah, there's places where contours which stay fixed on there. So one of the things that Mathieu wanted to do was calculate the positions of those nodal lines. All right, well, that was 1868. What do we think of this now? The Mathieu differential equation and the modified Mathieu differential equation occur in a wide variety of applications. We were first interested in a problem in blood flow where the blood vessel was being constricted to a shape that you could reasonably model as elliptical. And when you solve Laplace's equation in those elliptical coordinates, you get Helmholtz's equation. And you use separation of variables on that, you get two differential equations. One of them is the Mathieu differential equation. The other is modified Mathieu differential equation. And the period pi and period 2 pi solutions on only those periodic solutions are known as Mathieu functions. And the solutions of the modified Mathieu differential equation called the modified Mathieu functions. Some people call them the radial and the angular Mathieu functions. These functions have a zillion applications, not just to fluid flow. They're useful in electrostatics, for instance, quantum mechanics. In some ways, they're being displaced by direct numerical solution of the original equations. Our methods for direct numerical solution are getting really, really good nowadays, but using Mathieu functions can get you spectral accuracy even for that, so that's not a bad thing. So here's the first few of the cosine-like Mathieu functions. This is Maple command plot sequence of Mathieu CE for k going from 0 to 4, and I've chosen the value 4.0 for the Q parameter. I'll talk about what the Q parameter is. And this is just a collection of cosine-like things plotted on the interval from 0 to 2 pi. Great, they oscillate. Yay. And of course I used the built-in Mathieu functions in Maple there. And what are Mathieu functions? What are the Mathieu differential equations? If you look at the second order linear, not constant coefficient differential equation, that is the Mathieu differential equation. Y double prime plus a minus 2q times cosine of 2x times y is equal to 0. Solution of that are going to give us, when a is an eigenvalue of that equation, it's going to give us a Mathieu functions. Wait, eigenvalue, a being an eigenvalue, normally people say lambda, but Mathieu wrote a, so we write a for the Mathieu eigenvalues, except when we write b. This is a Sturm-Liouville differential equation, and so Sturm-Liouville theory applies, at least when Q is real. We'll see that in a minute. So when you solve the Mathieu differential equation, you get Mathieu C and Mathieu S. Mathieu C is like a cosine, Mathieu S is like a sine. Mathieu C has value 1 when x equals 0, and its derivative with respect to x is 0 when x equals 0, and Mathieu S is 0 when x equals 0, like a sine, and its derivative with respect to x when x equals 0 is 1. So, great. Now, if we look at the modified Mathieu differential equation, well, instead of a plus a minus 2q cosine, it's got a minus a minus 2q hyperbolic cosine. But otherwise, very similar looking equation. And when you solve it, you see, oh yes, the same solution is the same, except it's not x in there, but I times x. Maple's square root of minus 1 is written capital I. You can change that, but I didn't do that. Tempted to change it now on the fly, but no, let's just keep going here. All right, that's Mathieu functions in Maple. Let's have a little historical digression. So Mathieu himself was born in 1835 and died in 1890. And those of you who want to do subtraction can figure out what kind of a score he racked up. Let's look a little bit at an obituary of Mathieu. The first line in this obituary looks a little bit strange to modern eyes. If it were asked what tyranny in this world has least foundation in reason, and is at the same time most overbearing and capricious, none could be found to answer better to this description than fashion. Okay, great. What does fashion have to do with mathematics? Down there, at the bottom, it says, you may be surprised to hear that even there in the scientific world, if you would please, you must bend the knee to fashion. So this obituary was well worth reading, and I recommend that you read it. But anyway, it seems strange. Mathieu's mathematical legacy is a mixed one today. He started as a pure mathematician, but he was unable to get the positions that he wanted. And so he switched to applied mathematics and mathematical physics. And he thought that would maybe be of more interest. But it still didn't work. He still was unable to gain a post in Paris, which is what he wanted. And eventually he settled for a position in Besançon, and later after that moved to Nancy. And it seems strange that reading the biography, you see that he felt somehow that he was always just short of winning what he really wanted. But his name is remembered, for instance, in the Maple help pages in two different ways. One for Mathieu groups, to the sporadic simple groups, and the others for Mathieu functions. So he actually did achieve quite a lot. We could go to the Wikipedia page, but I'll just skip over that for the moment. One reason we know Mathieu's name is that Whittaker named the elliptic cylinder functions, which is maybe a more descriptive name of these functions, and he named them after Mathieu. The period pi and period 2 pi solutions of the Mathieu differential equations are the Mathieu functions. They're like cosines and they're like sines, but more general in some way. If you want to learn the theory of Mathieu functions, the amazing and wonderful course of modern analysis by Whittaker and Watson is now legally and freely available, at least the early editions. The latest edition is still held at Cambridge, but amazing book, and really everybody who wants to know things about special functions should read that book. Whittaker's obituary reads differently to Mathieu's obituary. 22 pages of dense and interesting mathematics, not counting the frontispiece and not counting the 4 pages of citations to his work. So there's just a ton of stuff in Sir Edmund Taylor Whittaker's obituary. So I recommend that you read that. Let's look at another figure in the history of Mathieu functions, is Edward Ince. So again, if you're keeping score, up above, Whittaker lived for 83 years. But Ince only lived for 49. He led a short but interesting life. His biography is well worth reading, and so are the obituaries. There are two really moving obituaries of him, one by Whitaker, just up above, and one by A.C. Aitken. Aitken was a very famous numerical analyst, but one of the more interesting things about Aitken is that he won a Royal Society Prize for Literature for his memoir of the First World War entitled From Gallipoli to the Somme. Aitken served at both places, and he was from New Zealand. Very interesting man. But that's a digression. Aitken didn't do anything about Mathieu functions, and Aitken wrote an obituary of Ince, who did do some interesting things about Mathieu functions. So if you want interesting historical figures, Ince is worth reading about. But the real interesting person in the history of Mathieu functions is Gertrude Blanche. Gertrude Blanche's Wikipedia page has a ton of interesting stuff, and I won't click through that because I don't trust the video software to follow me from where we are to the Wikipedia page. It didn't work on the full screen mode, so that's why we're plodding through this thing clickety-click. But anyway, here's one of my favorite photos of Gertrude Blanche. This is from 1963 when she was receiving the Air Force Exceptional Service Award. And that was the same year she was elected to the American Association for Advancement of Science. Well, how did she get there? 1963 in the AAS, that was very well done. Her PhD in 1935 was on algebraic geometry. Great, wonderful style of mathematics. Later, she became perhaps the first of the new kind of numerical analysts. Maybe she was the last of the old kind, in charge of humans doing the computing instead of machines. But she was one of the first for using machines, too. She was the author of Chapter 20 in the Handbook of Mathematical Functions, which everybody knows as Abramowitz and Stegen. And that chapter was on the Mathieu functions. She wrote one of the first textbooks on numerical analysis, modern numerical analysis. She wrote papers on continued fractions and, of course, on Mathieu functions themselves. There's the Greer's 1997 paper from which I took that photo is that's in the IEEE Annals of the History of Computing. Blanche really has a substantial place in the history of computing for her role in the Mathematical Tables project. She also helped to found one of the modern journals for this, Mathematics of Computation. So there's a 1977 interview of her by someone, Henry Tropp, which is well worth reading. It's a really, you get a real sense of who she was and the people that she met. More details on her contributions to life can be found at this AMS volume, Pioneering Women in American Mathematics. So I want to say more because there's so much more. Some of the interesting things about mathematics at that time were actually social things. So the Mathematical Tables project in 1938, which when she became involved with it, was a work project authority, part of the New Deal, to get people out of the Depression. And one of the things that Gertrude Blanche did was teach people who really didn't have mathematical training how to do computation of serious mathematical functions by hand. And this was, okay, that's a social thing. In the 50s, after the war, there was question of Gertrude Blanche's loyalty. She was accused of being a communist because, well, her sister was a communist, a registered communist, and so she couldn't get security clearances for this. And she had to fight for her rights to do that. She fought for a hearing and won. And so she was allowed to continue to work on these projects. And later she wound up getting an actual security clearance and worked at Wright-Patterson Air Force Base, where she did a lot of her research work. for those of you who keeping score, she didn't quite make her 99th birthday. She was 1 month shy of being 99 when she died. But she kept working right up until the end, was working on Mathieu functions right up until the end. As I say, an extremely interesting biography. We'll see what she did for Mathieu functions, because her approach is the one that I followed. And we'll talk a little bit about exactly that. All right, now on to the mathematics. One of the things that Mathieu did, and Mathieu did really an enormous amount for these functions, he deserves the credit, is one of the things he did was he identified Fourier series for the periodic functions, which were the solution of the differential equations. And he identified them in the sense of computing perturbation expansions for them, valid for small q. So in Maple, you can just ask for these series. So you ask for the series in terms of q of Mathieu CE 0, the first one, which is sort of like the 1, cosine of 0x. And you see that, yes, to first order, it is 1. 1 plus something that depends on x times q, plus something that depends on x times q squared, etc. But then you realize that those somethings that depend on x are actually even cosines. Only cos 2x, cos 0x, 2x, 4x, 6x, etc. terms show up in there. And that's part of the definition of CE 0. It's an even function of period pi. And it corresponds, its eigenvalue is close to the 0 eigenvalue, which corresponds to 1, which is, so its series of that eigenvalue is minus 1/2 q squared plus order q to the 4th plus etc. As you can see, Maple knows these series built in. You can compute to whatever order you like. So in comparison, the CE function that's like cosine 3x, you say Mathieu CE 3qx, and you take the series with respect to q, and you get a cosine 3x plus an order q term plus an order q squared, etc. And the third eigenvalue, the frequency of cos 3x is, of course, 3 squared is 9, so we have the series of the eigenvalue associated with this one is 9 plus 1/16 q squared, etc. Mathieu knew all of these, and he had a general formula for the series expansion of the eigenvalues, which is a bit tricky to make it work because it's valid only for a little while unless you've got the right term. It's hard to explain. But generically, there's a generic formula which has got terms like 1 over g minus 1 in it, g minus 2, so you have to work at a high enough frequency so that those terms don't matter, which is kind of strange. But Mathieu got it right. Great. Perturbation expansions are fun and useful, and Fourier series are wonderfully useful. But let's see what Ince did. Ince took the Fourier series and said, I can write that in terms of determinants. He wasn't thinking in terms of eigenvalues. He was thinking in terms of determinants. And wrote down tridiagonal matrices, which turn out to be a very, very effective way to compute eigenvalues nowadays. So here's a truncated tridiagonal matrix corresponding to the even period pi eigenvalues, so cosine 0x, 2x, 4x, etc. So we plunk this matrix down, and I chopped it off at 6 by 6 just so that it'd fit on the page. And if we compute the eigenvalues and the eigenvectors of that little matrix, we actually get the first 4 Mathieu eigenvalues of the differential equation to quite high precision. So the first one in particular, only the last 4 digits are wrong. Maybe the last 5 digits are wrong. And even the big one, you have 5 or 6 digits correct. And that's only with a 6 by 6 matrix. If you want more digits correct, just take a bigger matrix. The infinite tridiagonal matrix is a very nicely behaved one because the entries along the diagonal grow like the squares of integers, actually. It's squares of twice the integers, and so they grow quite quickly, and so the eigenvalues cluster around those points for small q. Well, okay, where does that matrix come from? It's just a trig identity. If we multiply cosine 2x times cosine of anything times x, where n is an integer, we get cosine of the anything minus 2x times cosine of anything plus 2x. So that just shifts the frequency down and up. If n is 1, or if, then something else has to happen. It doesn't go down to minus when it comes back to 1. So at one edge of the matrix, it's going to be something special. But okay, what about sines? Cosine 2x times sine nx does exactly the same thing. It just shifts the frequencies by plus or minus 2. So if you plug in a sum of, say, odd sine functions into the Mathieu differential equation, all you're left with, once you've done the multiplication of the cosine 2x times sines, is odd sines. And you collect up all of the odd sine things, the same ones, and you find that when you set all those coefficients to 0, it's just a purely tridiagonal system of equations. It's actually very, very effective. It's probably the most highly favored method for computing Mathieu eigenvalues today. Those matrices are symmetric. So if Q is real, that means all eigenvalues are real. And in this case, the eigenvalues are distinct and the eigenvectors are orthogonal, and Mathieu knew this without matrices. By Sturm's theory. Sturm was a relatively recent, near contemporary of Mathieu, and Mathieu cites Sturm's work and had to extend it a little bit. Sturm didn't do the case with periodic boundary conditions, but it works anyway. Okay, so Mathieu made that extension to periodic boundary conditions. And once you've got the eigenvalue, then the eigenvector is easy, and the eigenvector entries give you the coefficients of the Fourier expansions of the Mathieu function associated to the eigenvalue. For real Q, eigenvalues are simple and increase to infinity by the standard Sturm theory. And the eigenvector components, the entries in the eigenvector, they decay very, very quickly, so you can approximate Mathieu functions using only a few frequencies. And that's a victory for harmonic analysis. The inner product, the orthogonality of Mathieu functions is, completely unsurprising. It's just the weight function is just one, standard Sturm-Liouville theory. And so cos 2x, who cares about that? That just disappears with the usual trick. I linked to a YouTube video by someone named Juliet M. I just Googled Sturm-Liouville orthogonality, and hers was the first video that came up, and she was solving a midterm problem for her students there, and it's perfectly great. Hooray for YouTube. If you haven't taught Sturm-Liouville theory yourself recently, you might have forgotten how the tricks work, but they're not very hard tricks. They're kind of fun. And here we're using them, as the saying goes, in anger. Well, what about normalization? That says orthogonality, but doesn't say orthonormality. Conventions vary. Mathieu used a very weird normalization. Well, it's weird to modernize. For small q, the eigenvalue is nearly the square of an integer. For 3, we had 9. And the eigenfunction is very like a particular sine or cosine. And so he made the coefficient of that particular sine or cosine equal to 1 and divided by that and made everything work in that sense. And that was convenient for his perturbation computations. It was Ince who pointed out, sorry, even for real Q, for large enough real Q, the coefficient of that whatever term you're trying to divide by, that might be 0. And so it doesn't always work. There are exceptional points. So Ince instead said, no, let's normalize so that the integral of the square of the function is pi if k is bigger than 0. If k equals 0, you want 2 pi for the usual reason, same as in ordinary Fourier analysis. However, sadly for Ince, and sadly for many people lots of pieces of software, that normalization only works for almost all complex Q. There are isolated complex values of Q for which that integral of the square of the function is 0. It's possible for non-zero Mathieu functions to have 0 norm. Well, does that mean we made a mistake? We're supposed to multiply, not integrate the square of the thing, but integrate the square of the modulus? Why don't we multiply by phi conjugate? You go back to those standard tricks for orthogonality, and as long as Q is real, that works, because then you can multiply by the conjugate of the thing. Well, everything's real. It's all phi square and the conjugate are the same. But if Q is complex, then you can't do that trick, because the second equation that when you subtract, it has to be completely conjugated, and you have the complex conjugate of Q in it, not Q. And so that cosine 2x term, which disappears, doesn't disappear. So it's just not true that the functions are orthogonal when you have the conjugate. Okay, well, if we can't do that everywhere, what are we going to do? What we do is what's done in the DLMF, Digital Library of Mathematical Functions, where they call these functions C and S. They call them W1 and W2. You just normalize it by saying the C function, the W1 function, is like a cosine. Its value at 0 is 1, and the value of the derivative at 0 is 0, like the cosine. And the Mathieu S is like the sine, so the value is 0 at the origin, and the value of the derivative is 1. It's a little different to what Mathieu did, but this works because the solutions to the Mathieu equation are entire. So this specification is enough to say exactly which function we have as a solution to the Mathieu equation, and any other solution can be expressed as a linear combination of these two. And this is true whether A is an eigenvalue or not. So this works for the Floquet theory, works for all kinds of stuff. So that's what I do in my code, is I use this particular normalization. It looks like Maple uses this normalization as well, and it's true, but the Maple's Mathieu S and Mathieu C don't work for complex Q, which is too bad, just real. The SciPy code only works for real Q. MATLAB code only works for real Q. If you want complex Q, and we did, we wanted pure imaginary Q for our blood flow in ellipse application. We actually need it. We couldn't use that software. So here's my code. We'll use a little bit of it, but both 1 and 2 is the main one. That computes both W1 and W2. That is Mathieu C and Mathieu S. But I'm not going to use the eigenvalue technique of Ince. Instead, I'm going to use the continued fraction technique of Blanche. Blanche worked in an era before eigenvalues were easily solved. The QR algorithm was invented independently in 1961 by John Francis and Vera Kublanskaya. 1961, 1960, about the same time when Blanche was winning this award. So it's possible, she might have known about the existence of these algorithms in theory, but this is long before LAPAC. So it's long before you had libraries implementing these wonderful algorithms. And let's face it, the matrix that we're looking at is very special. It's symmetric. It's tridiagonal. It's not Hermitian. It's complex symmetric. If Q is complex, then that's a complex symmetric matrix. It's kind of fun. Leads to the indefiniteness. So Ince had found a continued fraction, which was equivalent to the eigenvector computation. Apparently Heine had also found that, but we think that was independent. But it was Blanche that turned that continued fraction into a practical algorithm. So how did she do that? She wrote down actually an infinite collection of continued fractions by you have this continued fraction equal to 0. Well, then you can invert one part of it and say this part of it has to be equal to that part. Oh, you don't like that? You can go down a few layers and invert and say these two parts have to be equal. So we have an infinite collection of continued fractions where we have an equation defining the eigenvalue. This is going to be 0. Given Q, the value of A, which makes this 0, is going to be an eigenvalue for the problem. And her algorithm, you need to decide whether you're dealing with an even function of period 2 pi, an even function of period pi, odd function of period 2 pi, odd function of period, whichever one I didn't say last time. And so she wrote down, it's called the M type. It's either 0, 1, 2, or 3. So we need to decide which of the continued fractions you're solving. And you need to have the special edge conditions for the tridiagonal matrix. They applied also to the continued fraction in here as well. So I implemented that. I wrote, it's called the Mathieu continued fraction. And I've given this one on this line for equation 17.2, I gave it the built-in Mathieu eigenvalue of index 2. So this is going to be of M type 0 is going to be an even function of period pi. And the value of Q is 1.0. It's not 0 is easy, but 1.0 is, maybe we could use the series. We don't know, but anyway, just go ahead and do that. And however Maple computes Mathieu A, it gives me a number. I put that into my thing. And I have the Q being 1.0. And the answer back from the continued fraction says the first part is 0 to 10 to the minus 14. Okay, great. So we've found a 0 of this function. What is all the other stuff that's coming back? That's 6 entries in a vector. Well, those are derivatives. If we're going to do zero finding on a nonlinear equation, it's helpful to have derivatives, and I went a little bit crazy and decided to give you not only t, but also t differentiate with respect to a, t differentiated with respect to q, twice with respect to a, once with a, once with q, and twice with q. And at the time, I was thinking about hand constructing series for those things. Turns out all I really needed in there is t, ta, tq, and taa. And those are enough to get a lot of things that we really want. But the TAQ and TQQ, they didn't hurt. All right. How do we solve nonlinear equations? We solve them typically by Newton's method. So once we've got a good approximation for a root, then we evaluate the function at the root, divide by the derivative of the function at the root, subtract that from the old approximation to the root, and we have a new approximation to the root. And so given good enough initial approximations for the root, we're going to be able to get convergent Newton iterations on here. This is such routine that I'm actually not going to talk very much about it. I'll show you some examples, but not anything interesting. But there is a problem. There are double eigenvalues. Those double eigenvalues are exactly the places where the norm goes to 0. We have eigenfunctions coalescing at that point. Mulholland and Goldstein were the first ones to find any double eigenvalue in the Mathieu equation, and I'll give you the values of the points. In the equation 18.2, we have the value of q being 1.4687 blah 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 times I squared of minus 1. So a purely imaginary q has an eigenvalue a is about 2.0886, and not only t, but the derivative of t with respect to a is 0 at that point. We have a double eigenvalue. Oh, so if we're going to solve for double eigenvalues, we can't just use ordinary Newton's method because the derivative that we're dividing by goes to 0. Gertrude Blanche and her co-worker used a quadratic approximation and solved the quadratic at every stage instead of using linear approximation. That worked great. And they used interpolation in Q to find the the value of Q for which you had a double eigenvalue. That's 1966. So quite a long time ago. Perfectly effective technology. Later, Hunter and Guerrieri, 1981, used what I think is a probably more effective method. You use two-dimensional Newton. So you're not solving for just A, you're also solving for Q. So you have two equations, T equals 0 and dt by dA equals 0, and you have two free variables, the value of Q and the value of A. So given good enough approximations for both of those things, you can go ahead and find highly accurate approximations for the double points. As far as I can tell, no freely available software will do this for you. The theory is 50 years old. More than that if you go back to Mulholland and Goldstein. So I'm a bit surprised that nobody actually incorporates it. Of course, if you choose your value of Q at random, you've got probability 0 of hitting a double point. But nonetheless, near to the double points, the standard methods for computing eigenvalues slow down tremendously. It's not a good idea to use ordinary Newton's method near a double point. Anyway, double eigenvalues are trouble. All right, now let's use my duct tape and bailiwick wire code. My code has no user interface. It's just meant to be used by somebody who's willing to experiment and to reach in and avoid the sparks and have it work. So Blanche said something really interesting in one of her papers about software. She said, some people like to use their software in a robot-like manner. Of course that's true. You want the software to push the button and have it go and work quickly, give you the right answer, and never come back and say out of cheese error or some other kind of strange thing. No, you just want it to work. You want to be a robot. My code is not robot-like. It's more like Blanche's code. Her code was meant to be used in a human supervised manner, and you interact with it. My tools for interaction are a lot easier than the ones that she had to work with. There's no question about that. And so I'm using purely in Maple code that solves double eigenvalue problems, finds double eigenvalues, and away we go. So how it works, I'll talk a little tiny bit about it later. It's essentially I solve the differential equation numerically, and this allows me to solve both for Mathieu functions and modified Mathieu functions. This is the solution for the Mulholland and Goldstein double eigenvalue point. The black is the real part of the solution, and the red is the imaginary part of the solution. And the little knots on the curve, those are the places where my numerical method step to, and the lines in between are drawn by two-point Hermite interpolation. I have very high order methods, and I have very nice, very beautifully stable Hermite interpolation on there. So it's actually really, I'm quite pleased with that stuff. But the Mathieu equations are hard in an interesting way, and we'll get to that in a second. So there's the solution, and I just to show you that the norm really is indefinite, I take my solution and I zip two things together. So I take the complex solution for, I think it's probably C0, which has merged to C2 at this point, and I multiply it with itself. So I zip A comma B goes to A times B, and I take W1 as A and I take W1 as B, and so I mash them together, and then I integrate the result. Because each piece is a Hermite interpolant, you can integrate the Hermite interpolants exactly, and it's a lovely way to do numerical integration of these kinds of things. All right, so we integrate this from 0 to pi, and we get an answer of minus 2.9 times 10 to the minus 15 plus 5.7080 times 10 to the minus 15 at the end. Okay, I'm sorry that the integral of w squared is 0 over there. Well, it's a complex function. There you go. So there's the demonstration. That's 0. Well, wait. You know, this is duct tape and baling wire code. How accurate was that? I used the default tolerance of 10 to the 4 minus digits, so that was 10 to the minus 11. All right. After it's computed, I sampled the residual at 52 points over each step. What do you mean residual? I differentiated my interpolant. It's a beautifully smooth interpolant on each piece. I differentiate that 2 times, substitute that in for y double prime in the equation. I multiply it by a minus 2q times cosine of 2x times y, and evaluate all that at all of those points, and I look at what's left over, and that's 10 to the minus 12 for the most part, up last interval about 10 to the minus 11. Great. My solution is as accurate as I wanted it to be. If I want more accuracy, I tighten the tolerance, and away we go. Let's have a look at modified Mathieu equations with the same code. So just to show you that we can do things at higher accuracy, I take 40 digits and I take 20th order. That's actually a 40th order method because I do series expansion at each point of order 20, and then I combine them to go over the steps. So I'm using a very, very high order method, and I integrate from 0 up to 3.25 times I. So now I'm integrating x going from 0 up the imaginary axis up to 3.25i. And I've got complex values of q and complex values of a. So I'm numerically integrating a differential equation in the complex plane. That's fine. We can do that. It's easy enough. Runge-Kutta methods would do that too. I wanted an interpolant that I was happy with, and this is a nice one. And I asked it to integrate with a tolerance 10 to the minus 16 in here, and the solution was quite quick. And here is the magnitude of the solution. The magnitude of the solution on a log scale goes up to 10 to the 8th. So Z is only just gone up the imaginary axis a little ways, and the value of the solution of the modified Mathieu equation has gone up to 10 to the 8th. Oh, what about the phase? If we plot the phase, we see the thing is winding around more sharply and sharply. And it turns out that Mathieu equations oscillate a lot going up the imaginary axis. So modified Mathieu equations have exponentially increasing frequency. And this means computation of them is inherently complex. I think the cost to solve Mathieu equations, modified Mathieu equations, for a very large argument is more than exponential. And you have to know your initial data if you're interested in any of these things to that amount of accuracy as well. So tough to do, but you can do it. All right, the Blanch and Clem double points. Blanch and Clem, 1966, printed a table of their double points. And there are a lot of them. I wasn't going to retype those things in, so we used optical character recognition. There were some really, really funny OCR errors. 6 got recognized as a Russian B. And, you know, there's the characters just show up in the table, and so you're trying to read these things in, and the code goes, ugh. So you have to manually edit the OCR recognition to get things that are actually digits. Anyway, once we did that, that was a lot easier than typing them in. We ran our two-dimensional Newton over each of those things, and they're correct to all figures. Gertrude Blanch was very widely recognized for careful work, for accurate work, and one of the reasons that the tables project was successful was because it was her guidance, and there's reasons for that. Okay, Great, double points. What do you do? We now got double eigenvalues. That means if two eigenfunctions coalesce, now we don't have completeness in our expansions anymore. What do you do? Well, it's exactly what you do for matrices. For the Jordan canonical form, you only have one eigenvector. Then you solve generalized eigenvectors. So we solve the same Mathieu differential equation applied to the unknown function u this time is equal to our coalesced eigenfunction. And this gives us another function that we can use in the expansion. And so here's an example where CE4 and CE6 merge. And here on the right, you see the generalized eigenfunction. You see, it doesn't disturb things at the boundaries. At 0 and pi, it has 0 influence. But in between, there's actually appreciable content. And so you actually need these functions. Okay, another fun little bit. I have no idea how long this video is going to be, but you guys can always run it at high speed. One really interesting thing that most people don't learn in our standard curriculum is that Newton's method works over formal power series. You don't have to just compute Taylor series. You can use it to compute Puiseux series, and you can use the same algorithm. You use Newton's method, just you need a little bit better accuracy for Puiseux series. So here's an example with two really simple functions. Let's take f being e to the y minus 1 plus x equals 0. All right, if x is equal to 0, then y equals 0 is the solution to that. E to the 0 is equal to 1. So our initial approximation has one term correct in its series. The correct term that's correct is 0. All right, we'll do 3 iterations of Newton's method on this. Yk is yk minus 1 minus f of yk minus 1 over the derivative of f at yk minus 1. And we take, at each stage, we take the series with respect to x. This is something that is easily programmed, is easy to be done, but I'm just going to use the built-in series in there. And so first iteration, you start with 0, you get just minus x. No, that makes sense because e to the 0 minus 1 is 0, and you get minus x. Great, and the derivative is 1 at the point. So now we have two terms correct, 0 and minus 1. We iterate again, we get y2 is 0 minus x minus 1 half x squared minus 1/3 x cubed. So we now have 4 terms correct, and the minus 1/8 x to the power 4 is wrong. So the number of terms in the series that is correct is doubling with each iteration. This is wonderful. It's actually nicer. Newton's method is nicer in formal power series than it is in numerics. But anyway, just to compare with the exact series, you see that after 3 iterations, we've converged to the first few terms. In fact, it would be correct up to order 8 if we work to that. I will working to the default order here, which is 6. That's fine. Well, I claimed that this worked for Puiseux series as well, and it does. So let's take the function y squared minus sine of x. So y squared minus sine of x equals 0. It means y is the square root of sine of x. And starting with an initial guess of 0 here won't work because the derivative is 0 at 0. No, we can't divide by 0, so that's a bad thing. So we need actually 2 terms correct in the initial series. 0 plus square root of x. So that's the first 2 terms in the Puiseux series expansion for square root of sine of x. That makes sense because sine of x is approximately x when x is small, so square root of sine x is approximately square root of x. Great. We do 3 iterations with that in the power series, and we compare that 3 iterations with the built-in series, and we see that we're correct up to order x to the 33 over 2. All right. So it's a little bit more than 16, order x to the 16. And that was pretty good with 3 iterations of Newton's method, starting with 2 terms correct. Then there would be 4 terms correct in the next one, except we lose one because of we're dividing by 0 plus a square root of x term. Great. Then we have 6 minus 1 is 5. Okay. And then we have 10 minus 1 is 9. Away you go. 3 kinds of mathematicians, those who can count and those who can't. All right. What about Puiseux series about the double eigenvalues here? Well, we can do that. So I can compute with Newton's iteration in series for the continued fraction equation. So I wrote another code that evaluates that continued fraction in formal power series. It's basically the same code. It's actually a little bit simpler because I was letting the series do all the derivatives that I was doing before. I'll show you the code if I have time. I computed the Puiseux series for all of the Blanch and Clem double points, which include the Mulholland-Goldstein one. So there's the series where you have a plus square root, and then you have a series where there's a minus square root in there. And I take the plus Puiseux series and plug it back into the continued fraction series, and we see that all of the coefficients of the resulting series for T1 are 0, but only the first coefficient for TA, the dt by dA, is 0 in there. And that's important. If there were more coefficients 0 there, this series iteration wouldn't work. But anyway, I think it's pretty cool that we can compute Puiseux series by Newton iteration about the double points. All right, concluding remarks. I could go on for a lot more time. One of the really cool things about Mathieu's original paper was that he used anti-secularity to enforce periodicity, and that's more than 15 years before Lindstedt. And the Lindstedt-Poincaré method is justly famous for solving differential equations by enforcing anti-secularity. I said we found eigenvalues by Newton iteration, and I said just get good estimates. I didn't tell you how to do that. There's some tricky stuff there, actually. I've said nothing at all about how I actually do the numerical method. It's a variable step size Hermite-Breshkov method. And variable order, I've used it up to order 80. I've used it up to 200 digits, and yeah, it works really nicely. It's almost as fast as a spectral method. Not quite as fast as a spectral method, but almost as fast. I said nothing about whether it's better than existing methods. And there's a good reason for that. One, the real reason is that for the real periodic solution, the spectral method of solving the eigenvalue problem, you get all the Fourier series coefficients, that's really, really fast. Turning that into something that works for modified equations, there's a trick with Bessel functions. And again, it's not clear to me that that's beatable by any method. But I wanted something that I could independently test and could use, especially that I could attack these double eigenvalues from. That's why I did that. I didn't talk about the method of root finding. We need to be able to root find in Q in order to match the boundary conditions on ellipses. Sorry, just going to have to wait for another day for those things. Some of this work was carried out when I was visiting the Isaac Newton Institute in Cambridge. It was on the Complex Analysis Tools and Techniques program, and that was fabulous. I really enjoyed that. Several people at MapleSoft have helped with programming and presentation tips. So Jürgen Gerhardt, John May, Eric Bostma, and most recently Paulina Chin. Thank you, Paulina. Thank you all. Some of this was joint work with Chris Brimacombe and Meir Zamir, my colleagues. My friend Martin Gander read an early draft of our paper and made many, many comments. And he said, "Oh, this reminds me of Chladni figures." So you should find out about Ernst Chladni and these early figures too. They're fun. References. Ramowitz and Stegen is online perfectly legally. And of course, it's been replaced by the Digital Library of Mathematical Functions. Chapter 28 on Mathieu functions was written by Professor Wolf, but quite a lot of the earlier work, of course, was based on Chapter 20 of Abramowitz and Stegen. So this talk is based on the paper Computation and Applications of Mathieu Functions, a Historical Perspective, which joint with Chris Bermacombe and Meir Zamer. I wrote a funny little paper where I just found a whole bunch of modes for the 5-3 elliptic drum, which is where that vibrating picture came from. A paper with Eric Postma on blends in maple, and that is the Hermite interpolation part. An inverse cubic iteration, which is an asymptotically faster method for solving nonlinear equations than Newton's method. It uses the same cost per iteration, but achieves order 1 plus root 3, which is about 2.73 instead of second order. So that's kind of fun. Now, I'm very proud of the fact that a version of that paper has now appeared in La Caseta de la RSMA, which is the Royal Society in Spain, Royal Mathematical Royal Society of Spain, and it's a paper in Spanish. So if you want to read a paper of mine in Spanish, away you go. Thank you for your attention.